All right, this one has something interesting happening in that I think it's the first one we've seen where the degree of the numerator is bigger than the degree of the denominator. But we're going to jump in the same way. We'll start by trying to factor the numerator. It looks like I can factor out an x, and I'm left with an x squared minus 3x minus 4. The bottom is already just a linear factor on its own, so you can imagine that that's x plus 1 times 1. Basically, an x plus 1 is the only thing I need to worry about there. I can do a little bit better on the top. I can factor that x squared minus 3x minus 4 into x minus 4, x plus 1, and this is quite interesting because I now see something that I would like to cancel out. And we've said already that you're allowed to do that, as long as you remember that the two are not technically equal if you don't keep track of the fact that you were not allowed to plug -1 into the unsimplified version of this function, and you would be allowed to plug it into the simplified version if you didn't force the domain restriction. So we have to force that domain restriction to match what we were looking at before. Okay, so what's really interesting in this one is there's no longer a denominator in our formula. So this is no longer looking like a rational function, even though I know that's what it came from, and I would still categorize it as that because it does have that hole in the graph. But what I'm looking at now is just a quadratic. It's an x squared minus 4x, and this can happen, and it's okay, and it'll probably freak you out and seem like it's really hard, but actually this is kind of delightful because quadratics are hopefully really comfortable and we're very good at graphing them. What I would say is that I'd still start by thinking about what are my zeros because it's factored. So I know that it crosses at 0, 0. So what I'm thinking of is x times x minus 4 equals 0. This is n of x up here just to keep track, which means x has to equal 0 or 4. So the y value will be 0 when the x value is 0 or when the x value is 4. So I have two intercepts. Thinking about multiplying this out, that x squared minus 4x, I can see that it's a quadratic that opens up. It's not flipped upside down. So I can get a pretty decent rough sketch just by doing this. So there's a pretty good rough sketch. What I'm missing is the domain restriction. So I've been told that x is not allowed to equal -1. So I'm going to extend this just a little more so I have some room to show. So somewhere around here, there should be a hole in the graph. And I know that its x-coordinate is -1, but you should be able to find the y-coordinate of the discontinuity. And you would do that just by plugging your x value into the simplified version of the function. So I'm looking right here. This is the simplified version of the function. What I've written for myself is x cannot equal -1. So it's like this big warning, warning, don't plug in -1. But really the way I would think about that is physically I can plug in -1, but I need to remember that for this to actually still be my original function n, I need to leave that discontinuity there. So I'm going to break my rule and plug in that -1 and say, okay, if I plug in -1, I get -1 times -5, which is +5. So the hole in the graph is at -1, +5. We can look here and say 1, 2, 3, 4, 5, and this is at 1, -1, 5. So your rational function can just look like any other kind of polynomial with a hole in the graph. That's one of the possibilities. And don't let it freak you out. It looks weird, but it actually, I think, is a little bit easier.